Hello, welcome back. Today we're going to take a look at the derivative of e to the x, or what we call the natural base. This was given to us by a German mathematician named Leonhard Euler. See how happy he always was. Look at his name. There's some smiles in there. Yesterday we talked about how the natural log of x and e to the x is our inverse. We're a little bit more on that in just a little bit. But right now let's review what e to the x looks like. This is my x. Say hello, x. E to the x is what we call an exponential function. Its domain, it's going to go from negative infinity to positive infinity. But the range, if you notice, it starts at y equals 0 and goes to y equals infinity. And that is because of this e to the x. If I think of my exponential function. If I pick values for x, like 0, I get 1. If I pick e to the negative 1, I get 1 over e. And even if I pick a really small one, like negative 100, I'm going to get 1 over e to the 100. Now, even though this is a very small number, it never reaches the x-axis. So in this case, the x-axis is an asymptote. This is our horizontal asymptote. You might recall from yesterday, when we did the natural log, we said the y-axis was an asymptote for us. So how do we use our inverse rule to go from back and forth between exponential and logarithmic form? And that's the idea of that natural log of x and e to the x are inverses. I can write this as an inverse by saying this. We are saying that e to the u equals b. I can write this as a log by saying the log base e of b is equal to u. We don't typically like to write log base e, so we shorten it to natural log of b equals u. And that's because it occurs often, so we just have a new name for it. Now, there is another way we can do this. The other day we talked about exponentiation. And another way I could write this, if I have e to the u equals b, I can just undo it by looking at the base. If I take the natural log of both sides, what do I wind up with here? I just get, well, natural log and e, because they are inverses, they cancel each other out. So we're left with u equals the natural log of b. This is very similar to that exponentiation we saw the other day when we had something like the natural log of x equals 3. We would e both sides. The natural log and e would cancel. We get x equals e cubed. Thanks. I do work out. So let's use these to solve some exponential equations. If I want to solve something like this, very easy, I want to get rid of the log. So I can use my log properties, or I can just know my log properties. I can just exponentiate both sides, like so. And by exponentiating, these cancel out. And we get 2/5 equals e to the negative 0.916. I'm thinking there should be an x in there somewhere. Maybe that should be an x right there. So we'll call that an x right there. So this is x. And then I can solve for x. And that's going to become 5/2. Just divide by 2/5. E to the negative 0.916. I don't know. All right. That one might be a little messed up. Don't take my notes. But let's take a look at number 2. We want to isolate our exponential. So I can add 6 to both sides. So I get e to the 2x. Add 6, I get 15. Divide by 3, I get e to the 2x equals 5. And now I want to undo this. So the best way to undo it, I can remember my log properties, but nobody remembers those. But I want to undo an exponential. Well, what undoes an exponential? It's inverse. For example, if I have x plus 3 equals 7, my inverse, I have to subtract 3. It's my additive inverse, and I get x equals 4. Well, same thing here. Exponentials have an inverse, and that is taking the log of the base. So I take the natural log of both sides. I get the natural log of 5. These undo each other because they're inverses, and I get 2x equals natural log of 5, or x equals 1/2 natural log of 5. And there's our answer. Likewise over here, try it again, you go. So pause it, take a second, try this next one here. So if I take the natural log of both sides, we get the natural log of 3. We get 2x equals natural log of 3. Divide by 2, 1/2 natural log of 3. And that's our review. That's all you have to know about exponentials and logs from pre-calc. Okay, not much. But now we're going to take a look at the derivatives. And these are easy. Anybody date somebody and they have an x they could just never get rid of? Welcome to the natural log. To take the derivative of the natural log base c, it's going to be its own derivative. We're not going to talk about why this is. To do this, we have to do a little bit more what we call what's called a logarithmic differentiation. We'll talk about that later on. But right now, let's just see right here. The derivative of e to the x is just its own e to the x. It's its own derivative. You can never get rid of it. It's like that nasty little x you can't get rid of. Now, likewise, over here, this is just talking about chain rule. And this is really kind of our rule right here. When we take the derivative, we get e to the u. But u is a function of x, so it's like u of x. So we have to take the derivative of u as well, du dx. That's just reminding us to take the derivative of our inside function. Both of these are pretty good to memorize. Just don't forget your chain rule, and you'll never mess these up. So let's take a look at an example like number 1. We want to find the derivative. So we have y equals e to the negative 2x. Well, my derivative rule, dy dx, my derivative rule says it's just itself, e to the negative 2x. Well, we are going to multiply that by the derivative of my inside. In this case, the inside is the power. There is my inside function. That's my power inside there. And the derivative of negative 2x, just negative 2. And there's your derivative. See how easy that is? Let's try number 2 here. Take the derivative. Well, 3 is just a coefficient. I can just leave that alone. The derivative, again, these are always going to be a chain rule. We're going to get e to the 2x plus 2 times, and now I have to do my inside. What's the derivative of 2x plus 2? But 2. You can leave it like this, or you can go, that's just 6e to the 2x plus 2. And there's your derivative. Ta-da! Easy to do. So pause real quick and try number 3 if you like. If you got y prime, I did y prime, I could use dy dx. We're going to get the own function back. The derivative of an exponential, we always get that exponential back. Times, but now we have to do the derivative of the inside. That's the exponent part. That's our chain rule. And this becomes 6x. 6x, we found it. And leave it alone. All right, let's take a look at number 4. Now be careful for number 4. If you notice, we are multiplying two functions together. This is our product rule. And if you forgot the product, remember that's f, the first time the derivative of the second, plus the second times the derivative of the first. So my first is x squared. So when I take the derivative, we should get the first, which is x squared, times the derivative of the second. Be careful, there's a chain here. E to the negative x times, what's the derivative of negative x? Negative 1. Don't forget your chain rule right there. Plus the second, e to the negative x, and then what's the derivative of x squared? Dos equis. Stay nerdy, my friends. And there's your derivative. That's it. That's your derivative right there. Piece of cake. Easy as pie. All right, number 5. Let's take a look at number 5 here. Oh no, this is our chain rule. This is our natural log. We definitely see a chain. And remember, the derivative of natural log of x, just 1 over x. So when I take the derivative here, we are going to get 1 over this entire inside, 4 plus e to the 3x. We just leave the inside alone. It's our chain rule, right? Multiply that by the derivative of the inside. This is that chain part. And what's the derivative of our inside? Well, 4 is just 0. E to the 3x, be careful, is e to the 3x. But we have another chain. What's the derivative of 3x? 3. And there's our total derivative. I'm going to clean it up a little bit. 3e to the 3x over 4 plus e to the 3x. And now if I really didn't like you, I'd make you do quotient. I'll make you take the second derivative. All right. Piece of cake there so far. All right. So number 6. All right. There are 2 ways we can do this. One, we can just power our through it. Option 1. It's natural log, so it's very similar to number 5. So I can go dy dx is 1 over e to the x cubed. The derivative of my inside becomes e to the x cubed times, be careful, there's another inside, 3x squared. I can leave my answer like this, but if you're really good, you notice those two cancel, And we're just left with 3x squared for our derivative. Now, option 2, you can use your properties. There is a property you might remember that says if I have the natural log of a to the b, I can write that as b natural log of a. I can do that here. I could rewrite this as x cubed natural log of e. The natural log of e is just 1. They are inverses. They just cancel each other out. So I'm really just looking at the function y equals x cubed here. When we take the derivative now, we just get 3x squared, which is what we had here. It doesn't matter how you did it. All 3 of these answers are acceptable. All right, number 7. This is the one on the last test and quiz that caused the most trouble. We don't like this power of 2 with sign. Please rewrite that. Don't make that mistake. I'm going to rewrite this as the sine of e to the x squared. And now this is our double chain rule. There's my outside. So that's going to become 2. Leave the inside alone to the first. And now I take the derivative of my inside. Well, the derivative sign? Cosine e to the x. And I'm still not done because I have another inside, and the derivative of e to the x is again just e to the x. There's our derivative. These ones are rarely very nice for us. So make sure you take the derivative correctly here. All right, last one for this video, number 8. Then we'll take a look at some applications here. Number 8, ready? I would recommend the properties here, and that says the natural log of a over b is the natural log of a minus the natural log of b. So I could rewrite this. This is not the derivative, but it's going to help me. The natural log of 2 plus e to the x minus the natural log of 2 minus e to the x. What this is going to do, notice if I took the derivative now, I would have to use quotient rule. And that just gets really nasty. We don't want to do that. This is going to avoid that issue. So when we take the derivative, dy dx, we would get 1 over my natural log derivative, chain rule, 2 plus e to the x, times the inside derivative, that's my chain rule part, e to the x. Minus, here we get 1 over the derivative, that's our chain rule, 2 minus e to the x, and now we do our chain rule part, the derivative 2 minus e to the x, negative e to the x. And there's our final derivative. Right there. Don't worry about simplifying. All right. Go to the next video. We'll take a look at some applications. I'll see you then. Bye-bye.